talk more about disinfection from a microbial perspective. Disinfectants and antiseptics are either biocidal, meaning that they kill the pathogen, or they're bacteriostatic, meaning they inhibit through their chemical activity, or metals can also have this kind of property. There are many different examples of disinfectants, from alcohols to chlorhexidine to triclosan to chlorine, various heavy metals, especially silver. Ethylene oxide is used in gas sterilization, has been a focus of a lot of interest. Can also be hazardous because it's a carcinogen. Peroxygens like hydrogen peroxide or ozone, as well as quats or quaternary ammonium compounds like benzalkonium chloride. So these can be used in a lot of different ways. And so some examples are germicidal ultraviolet radiation, GUV, or you might just say UV. And there are different kinds of UV, like UVA or UVC. There may be hydrogen peroxide vapor systems, steam sterilization, or other temperature or pressure-based methods, akin to pasteurization, are all part of ways that you can disinfect or decontaminate different pieces of equipment or areas, spaces. You might also think about water disinfection, especially if you're thinking about what comes out in terms of the effluent from hospitals. They're the classic physical and chemical processes of wastewater management, such as filtration, adsorption, coagulation, and precipitation. But increasingly, there may be photochemical processes, such as UVA, UVC, or solar. And some of these can even be operationalized in low-income settings. For example, the use of solar activity as a water disinfectant for drinking water. Electrochemical oxidation is also increasingly used. And so some of these technologies may combine different kinds of approaches in order to provide the decontamination that's needed. There are many different factors that influence disinfection, and this is really important to keep in mind if you are designing or part of a program to limit these infectious disease exposures. So the type of infectious agent is important. So enveloped viruses may be more labile, that is easier to get rid of than non-enveloped viruses. Anything that can form a spore can be harder to inactivate. And then there are some pathogens that have more innate resistance, like parasite oocysts are really difficult to decontaminate, as well as gram-positive bacteria tend to stick around in the environment longer than gram-negative bacteria because, again, they just have this intrinsic resistance. This can relate to the concentration of the infectious agent. So if you have higher concentrations, you may need longer inactivation times if you're using a disinfectant in order to reach whatever your target is, like a log reduction of X. So prior cleaning, especially, for example, of surfaces, can reduce concentrations, shorten inactivation times, and therefore limit worker exposure to the disinfectant agents that can, in and of themselves, be harmful. The presence of organic and inorganic material is really important because these can be physical barriers, and organic matrices can also provide some support for bacteria and other microbes and can reduce the ability of the disinfectant to actually reach them. And then further, the organic material itself can react with some disinfectants to produce disinfection byproducts. And so an example is chlorine, which is used in water disinfection, will react with organic material to form these potentially carcinogenic disinfection byproducts, including trihalomethanes, haloacetic acids, bromite, and chlorite. And then finally, physical and chemical factors can influence either the organism itself or the activity of the disinfectant. And so temperature and relative humidity can impact microbial survival. So if it's just right for the bacterium, it may actually multiply at a faster rate. And both of these, temperature and relative humidity, as well as things like pH and water hardness, can impact disinfectant activity.